Hey everyone, welcome back to another MCAT Shemmassian workshop. My name is Farhad and today we're exploring a high-yield Chem Phys MCAT passage that's going to be pertaining to infrared fluorescent photodynamic cancer therapy. We'll read the passage paragraph by paragraph, discuss the figures, and we're going to go into all of the questions complete with explanations. Let's get started. Before we jump straight into the passage, we just wanted to say, we're going to go through this passage and there's going to be some questions here, but you can actually find over 4,000 MCAT practice questions on our MCAT question bank. Today we're only going over a couple of them, but you can find a ton of them over at Shemmassianconsulting.com. So let's jump right into paragraph 1. It states, photodynamic therapy, PDT, is an attractive, non-invasive technique for treating cancers. 2 steps are involved in PDT, including Step 1, delivery of a photodynamic agent to tumors. And Step 2, irradiation of tumor sites with specific light to activate PDT agent, followed by reactive oxygen species generation that triggers cancer cell death, and that is ROS. So, with these type of passages, there's a couple of things that I like to pay attention to. The very first thing is, anytime I get experimental procedures, I want to pay attention to that. What are the steps? I want to pay attention to that because that to me is the flow of the experiment. These type of passages or these type of paragraphs are important because sometimes you'll get questions that ask why a certain step happened. They're testing your understanding of the procedure itself. They're also testing to see, are there any buzzwords in there? Do you know what those buzzwords are? Can you picture what this experiment looks like? What happens if they tweak a certain step in that experiment? What happens if a step in that experiment is skipped or it doesn't work? Do you understand why this technique is happening or what the process is going on? So for this type of passage, I really like to pay attention to the steps, and I really want to pay attention to what exactly is happening here. Can I picture this? So let's see if we can pick up on the keywords, right? Some words that I might highlight would be photo in photodynamic therapy, non-invasive, treating cancer, 2 steps. I'd also want to get agent to tumors, irradiation with specific light to activate agent, followed by ROS. So what that's going to tell me is that this passage and this paragraph is really about light. We're using an agent to apply to the tumors. We're going to shine some type of light on it, and it's going to activate the agent, leading to ROS, and that's going to lead to cancer cell death. So to put that into some type of visual, God forbid I was to have some type of skin cancer on my skin. So if I have it on my wrist here, what I'd be doing is saying that I have a therapy. This therapy is a non-invasive technique. It does not require any cutting. It is non-invasive. I'm trying to treat this cancer. So there's 2 steps here. I want to deliver the agent. Let's say it's some type of cream. I want to deliver this agent to the tumors, and I'm going to irradiate it with some type of specific light. Let's say it's like a black light or some type of flashlight, right? So I apply this cream non-invasively, the agent to the tumor site. I'm going to irradiate it with some specific type of light, and that's going to activate the agent. That's going to activate the cream that's just sitting on my skin, on the tumor site. That is going to be followed by ROS generation, and then that's going to lead to cancer cell death. So even when I'm doing these passages, I'm thinking of things in a very objective way. Apply a cream, shine it with light, ROS equals good. ROS equals cancer cell death. So that's how I'd be doing paragraph 1. Let's jump into paragraph 2. It states, near infrared fluorescent dyes like heptamethane, cyanines, H-cyanines that can absorb and emit light in ranges from 700 to 1,000 nanometers are good PDT agents for tumor detection at millimeter depth. Researchers developed cyanine-based theranostic probes, MPIP, I'll call it MPIP for short, that has a molar mass of 1,087 grams per mole. And that's going to be for IR fluorescent imaging and PDT that's aimed to target cancer cells. This MPIP was synthesized via conjugate addition reaction between the original molecule and N-methylpiperazine using a reaction scheme that's shown in figure 1. So this paragraph is a bit of a tongue twister. It's got a lot of interesting words, a little, some difficult things to verbalize. And what tends to happen in these type of like very heavy, like organic passages or math passages is that they start throwing out a bunch of really tough words, some molecules that maybe you don't know what they look like, and they try to confuse you. They try to make you feel like you don't know what they're talking about. Because in reality, right, I've never seen what a H-cyanine methyl, a methylpiperazine might look like. I don't know what those look like, but I do know that it's a molecule, and I know that it's shown in figure 1. And so to do these passages, you really want to focus on simplification. How can I read this in a nice, simple way? How do I focus on the root of what is being taught here? So again, let's focus on some of the keywords. Some of the things that I might highlight would be that there are these fluorescent dyes. So it would be a fluorescent dye that can absorb and emit light in a range of 700 to 1,000 nanometers. I might highlight a millimeter depth. I'd also highlight that MPIP has a molar mass of 1,087 grams per mole. I might also highlight that MPIP was synthesized via conjugate addition. And that would be about it. I'm really trying to focus in on the things that kind of distinguish certain molecules or compounds, right? So I really try to focus in on what information am I given about MPIP specifically. I'm given its light range that it would do well in. I'm given the depth that it would work well in. I'm given its molar mass. I'm also given the reaction that it was synthesized. So I'm really trying to focus in on almost characterization, as well as I'm trying to focus in on terms that I'm supposed to walk into this passage knowing. What is the content that I'm supposed to know? I know that when I see numbers, I could get questions on the math and physics or general chemistry or organic chemistry. I also know that there's terms like conjugate addition, molar mass. I know that absorb and emit. I know that these are terms that could have questions rooted in them. So I'm trying to pick up on those. I call those almost spicy words. I call them miscellaneous facts. They're these little facts that are sprinkled into the passage, and it's up to us to pick up on those. So let's jump into figure 1. Hopefully you guys recall that with figures, tables, any type of graph, we really don't want to spend too much time on it. There's a couple of things that we're really trying to focus on. What's the title? Are there any axes? Is there any independent or dependent variables? Are there any trends? Very, very clear, distinct trends that are present? And is there statistical significance? These are the things that I'm trying to look for. And I'm trying to do that really fast. I just really want to spend a couple seconds on a figure. If I'm unable to do that, if those things are not present, I look at the title, I try and figure out exactly what's going on here. And besides that, I just want to move on. I want to know what information was in that figure. So if I was to get a question on it, I'd know what figure or what graph to go back to. So I'm really focusing on organization. That's what I'm trying to pay attention to. And so with this figure, the figure title says chemical synthesis of MPIP. And keep in mind in the passage, it did tell us MPIP was synthesized via a conjugate addition reaction, and it was between these two different molecules, the original molecule and the N-methylpiperazine. And so when I'm looking at this graph, right, I only really want to focus in on, is there axes? No. Is there independent and dependent variable? Not really. Is there statistical significance? No. But can I tell something very, very clearly that there is something changing? And the answer to that would be yes. I see that in the middle of the molecule, there's a chlorine, and on the MPIP molecule, there's this new ring with nitrogens on it. And so that's what I know that the difference is. I had the original molecule with chlorine, and the new molecule has an MPIP. So chlorine left, a new molecule was attached. So that's about the extent that I really want to spend on this figure. Now let's jump into paragraph 3. The passage says, to test its properties, a stock solution of MPIP was prepared by dissolving 2 milligrams of MPIP with methanol in a 3 milliliter standard microvolumetric flask. Subsequent UV, Vis, and IR fluorescent measurements were performed by using the appropriate amount of this stock solution. This is a pretty nice, easy, straightforward paragraph. I think the only things that I'd be paying attention to here are just some of the numbers. We can see that and the things that I would highlight here would be 2 milligrams MPIP, methanol, 3 milliliters. And that's about it. Again, I want to focus in on simplification. I want to focus on organization. What does this information have for me? It has this information of getting methanol, dissolving it, and mixing it with methanol so that we could do different measurements. That's all I really want to focus in on. Now let's jump into paragraph 4. It states, optical properties of the dyes were found to be dependent on the pH of the solution, as shown in figure 2. MPIP absorbed light from the visible to IR region, which is from 500 to 920 nanometers, peaking at 860 nanometers under pH 7. pH-dependent activity could be the result of an intramolecular charge transfer in MPIP. So again, let's focus in on what's the key thing in these paragraphs. What is in this paragraph that makes it unique to other paragraphs? And some of the things that I would highlight here would be, we're looking at optical properties. It's dependent on the pH. We also see that it's talking about figure 2, as opposed to the other paragraphs that might have been talking about paragraph or figure 1, right? So paragraph 2 indicated it was talking about figure 1. So when we get a question, if it's talking about maybe the molecule of MPIP, we know we could go 2 places. We could either go to figure 1 itself, or we could go to the paragraph 2. If we get a question regarding figure 2, and it has to do with optical properties or pH, again, these are 2 things that were not talked about anywhere else in the prior paragraphs. We would know that we'd have to go to either paragraph 4 or figure 2 itself, which we'll be coming up to. Other things that I might highlight would be that the IR region is from 500 to 920 nanometers. Again, this is something that you should come into the passage knowing, but in the case that you don't, it's helpful information possibly. And I'd also get peaking at 860 nanometers under pH 7. The final thing that I would highlight is that this pH-dependent activity, and I would also highlight intramolecular charge transfer. Again, why those things might be important for me is that they are miscellaneous facts, they are spicy words, they are these terms that kind of have some content related to them. We should walk into the passage knowing what intramolecular charge transfer is, what pH-dependent activity could be. We're also given these numbers, and these numbers could help us out with some math questions in the future, or be able to help us look at figure 2 and understand it better. Now, let's jump into figure 2. So again, we want to do the same thing. We do see some figure title. So the figure title says, visible IR spectra of MPIP in environments of different pH from 3 to 12. We also see that this has 2 different axes. We have absorbance, and we also have wavelength. We also see that when we're looking at the graph, there's no statistical significance here, right? There's nothing that's showing any type of error bars. There's nothing showing stars or p-values. So you're assuming that everything is going to be significant if it looks significantly different. And in this case, there should be a couple of groups that do look fairly significantly different. In this case, what I'm seeing is, again, we're looking for similarities, pairs, and differences. Let's just start off with some of the bunches of the 3. If we look at the pink, red, and orange lines, what we would see here is that the similarity between those is that they're very low pHs. They're very acidic. What we would also see is that pHs, the light green and the more vibrant green, those ones are pH 6 to 7, so they're fairly neutral. And then we have about 4 to 5 more lines, and that is the blues and the purples, the blues and these violets. And that goes from pH 9 to 12. And we can see that for each one of these three groups, there's a range that the wavelength is in. Keep in mind, paragraph 4, the paragraph we just came from, indicated that M-pips absorbed light from the visible to IR region. It was peaking at 860 nanometers under pH 7. So when we look at this graph, we can find that exactly in the figure. And so what we're doing here is we're combining the paragraph information with the figure data. And so we're trying to draw conclusions. We're trying to see the visualization of the information in the passage. Now let's jump into the final paragraph, paragraph 5. It states, in vitro experiments were performed to confirm the application of MPIP in cancer cell treatment. Colocalization experiments indicated that the probe prefers to accumulate in lysosomes with less preference on the mitochondria. What that tells us here is that this paragraph, again, isn't super dense. It's not got a ton of information. It's very different from the other paragraphs, right? There's no math, but what there is a couple of spicy words, a couple of miscellaneous facts. There are some terms here that have some content rooted in them. And again, maybe potentially there might be some questions that might arise from it. What those things might be and things that I would highlight would be in vitro experiments, colocalization experiments, probe accumulating in lysosomes, and finally, less preference for mitochondria. Again, there's just some key terms here, some key terms, key concepts, key types of experiments that we should kind of walk into this passage knowing. And with that, we're finished with the passage. I really hope that breakdown was including some new strategies or new ideas of things to highlight, things to pay attention to, and maybe some things that you can implement into your own passage breakdowns. Before we jump into the questions, I also wanted to just add, if you're looking for more information on MCAT buzzwords, do check out the comprehensive list of high-yield key terms. They're going to be listed at the bottom of each content unit in our MCAT Premium Content Hub. Now with that, let's jump into the questions and explanations. All right, so let's jump into question 1. The question states, what was the molarity of the stock solution of MPIP used in the optical activity experiments? So recall that when we're doing questions, we're always looking for keywords. We're looking for, sometimes I call them puzzle pieces, sometimes I call them crumbs. Pretty much what they're telling me is keywords that would help me navigate to certain areas in the passage, or keywords that's going to help me answer the question by using the answer options almost as a reference. So when we're doing these questions, what are the keywords here? In this question, I would say that it would be molarity, stock solution, MPIP, and optical activity experiments. The reason why some of this is important is because if we're looking for molarity, we know what units those should be. How do we calculate molarity, right? So we should know that. We should also know that stock solution and optical activity, specifically of MPIP, was referred to a very specific paragraph. That paragraph was going to be paragraph 3. And so knowing that, we would go over there and we'd pick up I'd call them givens. In physics, we call them givens. It's any numbers that would be pertinent or important. When looking at our givens, we're told that we have a stock solution of MPIP, and we dissolved 2 milligrams of MPIP with methanol in a 3 milliliter standard volumetric flask. When we come back to the question and the answer options, we'll see that the answer options all have something in common. So we'll see that 2 of the answer options, answer option A and B, have 6.1 times 10 to the negative 4 and 1.8 times 10 to the negative 4. So they have the same exponent. When it comes to answer option C and D, they also have something in common. They have times 10 to the negative 7 in the exponent. We might also see that there's another pair that we can make here. We could pair up A and C because they both have 6.1 in their beginning. We also can see that B and D have something like 1.8 in their beginning. So what I would be asking myself is, what's the simplest way of doing this? Would it be trying to calculate the exponent? Would it be trying to figure out, is it -4 to -7? Is it a really small number, or is it a really, really, really small number? Or is it something with a 6 versus something with a roughly 2, right? If we were to move over the decimal place and we were to round things out, it would be something roughly with a 6.1, which again would be roughly 6, and 1.8, which would roughly be a 2. And so I'd be thinking about, how could I narrow this down? How could I simplify this? And so keep in mind, the passage does state the molecular weight of MPIP used was 2 milligrams, and it created a stock solution along with the volume of liquid. That weight was dissolved in 3 milliliters. So molarity is defined by the number of moles of a given substance per liter of a solution. We can calculate that by dividing mass by molar mass, then subsequently dividing by volume of a liquid. So what that is we're going to be doing 2 times 10 to the -3 grams divided by 1,087 grams per mole divided by 3 times 10 to the -3 liters. And what that would give us is roughly 6.1 times 10 to the -4 molarity. What we can do again is, we can do this without a calculator, and we can tackle things based off of base values and significant figures. So first, we might want to notice that 10 times 10 to the -3 exists in both the numerator and the denominator when we wrote out that equation. So as a result, both of those numbers can be canceled out. What would be remaining is 2 divided by 1,087 multiplied by 3. So we have 2 in the numerator, 1,087, and 3 in the denominator. And that would approximate as something that is around 2/3 times 10 to the -3. 2/3 is about 0.66. And 0.66 has a 6 in it. It's very close to a 6, right? 0.66, if we move the decimal over 1, it would be 6.6. And again, 6.6 is really close to 6.1. And so for this question, our correct answer is going to be 6.1 times 10 to the -4 molarity. And hopefully, again, what we showed here is that there is ways to use some strategy here to simplify your answer picking process. Now let's jump into question 2. It states, what is true of the MPIP molecule? Statement 1 states, in HNMR spectroscopy, it will produce a shift between 0 and 2 ppms. That's parts per million. Statement 2, it says, in IR spectroscopy, it will produce a broad peak at 3,300. And in HNMR spectroscopy, this is statement 3, it says that it will produce at least 1 singlet peak. The interesting thing here is now we're talking about different types of spectroscopy and the different types of results that we would get based off of that spectroscopy for the MPIP molecule. What we should be thinking is, where would this information be referring to? How would I know about HNMR spectroscopy or IR spectroscopy of a molecule? Where would I get that information from? Keep in mind, figure 1 and paragraph 2 were where they started talking about the characteristics of MPIP's molecule. And so when we're answering this question, there is some content that is important here. This content is that we need to know these different types of spectroscopy and the results from them, right? So we should know about HNMR, what creates this 0 and 2 ppm. We should also know what other types of ppm ranges would be available and what the characteristics of those molecules would be. For statement 2, we should also know, like this one's asking us about 3,300, a peak at 3,300, but then what about other peaks? What about broad peaks? What about narrow peaks? What about stretches? Do we know the other IR regions for IR spectroscopy and what their functional groups would be for that specific range? If not, those are things that we should study. So to answer this question, we can go statement by statement. First, statement 1, this one is going to be that if H&MR spectroscopy signals that would have an appearance between 0 and 2 ppm, what that means is that you're usually going to come from protons that are attached to sp3 hybridized carbon atoms. In the case of this molecule, in figure 1, so in figure 1, what we're going to see is that MPIP, we do have sp3 hybridized carbons. For example, the methyl groups in the structure are sp3 hybridized, and their protons would definitely show up in that 0 to 2 parts per million range. Now on to statement 2. This one is going to be incorrect because it says something about a broad peak at around 3300. Well, in IR spectroscopy, that kind of peak is usually characteristic of a hydroxyl group or an OH group. However, this molecule doesn't have that hydroxyl group, so you wouldn't expect to see that broad peak. And that's why that statement's not going to hold up. Lastly, we have statement 3. And this statement 3 is going to be that to see a singlet peak in H&MR, the proton group in question should be attached to atoms that don't have any neighboring hydrogens. So fully substituted atoms in this molecule, one of the methyl groups is attached to a nitrogen in that M-methylpiperazine ring. And that ring, that nitrogen, is fully substituted, meaning that it has no hydrogens attached to it. So because of that, that methyl group isn't coupled to any neighboring protons. So that'll only give us a singlet. So because of that, we're going to have statements 1 and statements 3 that are going to be true, and statement 2 being false. And for that reason, statement 1 and 3 are true, therefore answer option C is going to be correct. Let's jump into question number 3. It states, what is the energy of a photon that's required to yield the greatest absorption by MPIP at physiological pH? Again, with these type of questions, we really want to be paying attention to keywords. Some things that I might highlight in the question would be energy of a photon, greatest absorption, MPIP, and physiological pH. Now we would look at the answer options, and again, we'd look for any type of similarity, any type of pair, any type of trend. And with looking at these answer options, there is a couple of things. You might notice that answer option A and D have some type of pair, and that pair is that the front part has a 2.3 to their value, so about 2.5. What you might also notice is that answer options B, C, and D have something in common, and that is the exponent of times 10 to the negative 19. We also should notice that A, B, C, and D, they're all in joules, and we're solving for energy. Keep this in mind, we're solving for energy for the greatest absorption at physiological pH. What's physiological pH? Around 7. So now when we start to solve this question, we should be thinking, okay, where would we get this information from? Where did it talk about characterizations of energy or pHs? And what we should be thinking is that information started to show up in figure 2 and the paragraph right before that. So when we're solving this question, we should keep in mind that it told us in the passage that at around pH of 7, there is a peak at 860 nanometers. And so that's where that maximal absorbance is coming from. So if we have a photon that yields a maximal absorbance, that would require that specific wavelength. That wavelength was 860 nanometers. So using the relationship that energy of a photon is equivalent to Planck's constant is 6.6 times 10 to the negative third times frequency. That would give us an equation that says E is equal to HF. HF is equal to HC over lambda. These are very, very, very common equations that tend to show up on the MCAT, so you definitely want to have these memorized. So now if we were to start filling in this information, we would have 6.6 times 10 to the negative 34 multiplied by 3 times 10 to the 8, divided by 860 times 10 to the negative 9. And what that would give us is roughly 2.3 times 10 to the negative 19 joules. That would be answer option D. Now let's jump into question 4. It states, according to the results of the experiment, at which pH is the absorbance of light by MPIP redshifted by the greatest amount? We look at the answer options and we have pH range 3, 6, 7, and 12. So we have ranges that stem from very acidic, like 3, pretty net neutral, B and C, and then 12, pretty basic. And so a thing to keep in mind here is similarities, pairs, and differences. We have 1 acidic, we have 1 basic, and we have 2 that are neutral, or fairly neutral. Now, a question I'd be thinking to myself is, where would I even be getting this information from? The question again is asking us about the greatest amount that something would be redshifted, and at what pH that would be. If we're looking for something that would have the greatest amount of redshift, well, a redshift and some type of thing that would give us an indicator of the greatest amount of that shift, we probably want some range in that graph that would be pretty distinct from the other ranges. What I mean by that is, if you have 2 answer options that look the same graphically in a figure, how would we be able to tell them apart for the answer? So what I mean by that is, answer options B and C, while they are 2 different pHs, they also have the same graphical representation, as in they're bunched together in the same wavelength range. So how would you be able to tell them apart? How could you pick answer option 6 over 7 or 7 over 6? You wouldn't be able to. So immediately, knowing that our answer has to come from figure 2, or the paragraph right before it, we'd have to cross off answer option B and C. And we'd be left with only answer option A and D. And so now all we have to be thinking about is, which one would be redshifted? Would it be the most acidic range, or would it be the most basic range? And so keep in mind that for something to be redshifted, that means that a waveform in question must be displaced towards the red end of the spectra. And because red light has a lower energy than other light in the visible spectra, it's represented by longer wavelengths. So when we look at figure 2, we can see that as pH decreases, or as the environment becomes more acidic, MPIP begins to show maximal absorbance at those longer and longer wavelengths. And so the wavelengths that are represented lower levels of energy and a resulting redshift. So the greatest magnitude of the redshift occurs at pH 3. A blue shift, on the other hand, which also represents shorter wavelengths, that shows high energies. So short wavelength, high energy, and that is the difference between a blue shift and a red shift. These topics are typically coupled with Doppler effect. So changes in frequencies or wavelengths and how that would affect different energies and different wavelengths, frequencies, things like that. And so as this figure is showing, as the pH becomes more basic, the maximum absorbance takes place at these shorter wavelengths. That would result in a blue shift. And so for this question, our answer is going to be A. We're looking for the greatest magnitude of a redshift, and that would be at a pH of 3, something very strongly acidic. And finally, let's jump into the last question, question number 5. It states, of the following options, what would be the most effective method to separate a mixture of MPIP and its original molecule? We have a couple of different answer options here. We have anion exchange column chromatography, cation exchange column chromatography, we have Western blot, and we have fractional distillation. And so again, we're looking for similarities, pairs, and differences. This question is fairly content related, but we do need to be able to look at those figures and be like, well, figure 1 had information about its original molecule and MPIP. What were the differences between them? And when we look at the answer options, there is a pair here, right? We do have differences. We have anion exchange and cation exchange. And what that usually tells you is charges. Was there a massive difference in charges? in MPIP in its original molecule? And the answer to that would be no, right? Where did we talk about anion or cation exchange or some type of ion exchange? And so for that reason, we'd be able to cross off answer option A and B almost immediately. The only options that would be left would be Western blot and fractional distillation. And Western blot has to do with proteins, and fractional distillation has to do with splitting molecules or compounds that are pretty similar. So the question is, are the molecules fairly similar? Would we be using fractional distillation? Or would we be looking at a protein and separating things or comparing things that are proteins? Well, did we even talk about proteins at all in this passage? The answer to that would be no. So for that reason, we take out C, and we'd be able to pick fractional distillation. Again, these molecules were very similar. There was a very small change. We had a chlorine versus a ring that was being attached. And so in this case, we would be using answer option D, fractional distillation, as the most effective method to separate a mixture of MPIP. And with that, it looks like we survived to the end of the passage. That was a pretty dense one. And so thanks for joining. We hope that this walkthrough was helpful in your MCAT journey. If you're looking for more practice resources, you can visit our MCAT question bank or our premium content hub for thousands of sample problems. Or if you want a more personalized approach, our MCAT experts provide one-on-one tutoring as well as individualized study schedules and test-taking strategies that go a step further than just content review. Check out our website to learn more, or feel free to drop a comment here with any suggestions or questions that you may have. Happy studying!